Tonight, we're going to explore something that's been a dream of humanity since we first looked up at the stars and realized how far away they are. Traveling at the speed of light. It sounds simple enough. Light moves at about 186,000 miles per second. And if we could somehow match that speed, the galaxy would open up to us. We could reach distant stars, explore alien worlds, maybe even find life beyond Earth. But here's what most people don't realize. If you actually could travel at light speed, the universe wouldn't work the way you think it does. Time wouldn't flow normally. Space wouldn't look the same. And the journey itself would be nothing like you imagine. By the end of tonight, you're going to understand what would really happen if you traveled at the speed of light, and why it might be the strangest journey possible. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something you already know. Speed. You understand speed in your everyday life. When you're driving on the highway at 60 miles per hour, you know what that feels like. The landscape slides past your window. Other cars overtake you or fall behind. You can speed up or slow down as needed. Speed is just distance divided by time. How far you go in how long. Simple mathematics that's been understood for centuries. Double your speed, and you cover twice the distance in the same amount of time. Triple your speed, and you cover 3 times the distance. This relationship is linear and predictable. Nothing strange happens. The faster you go, the more distance you cover in a given time period. That's true whether you're walking at 3 miles per hour or flying in a jet at 600 miles per hour. The relationship stays the same. But here's where things start to change. As you approach truly high speeds, speeds that are a significant fraction of light speed, the universe starts behaving differently. Not because the universe changed, but because you've been living your whole life at such incredibly slow speeds that you never noticed what the universe actually does at high velocities. Light travels at approximately 186,000 miles per second in a vacuum. To put that in perspective, light can circle Earth's equator about 7.5 times in a single second. That's almost incomprehensibly fast by everyday standards. A passenger jet flies at about 570 miles per hour. At that speed, it would take the jet about 43 hours to circle Earth once. Light does it 7.5 times per second. Light is roughly 1,170,000 times faster than a passenger jet. Think about what that means. If you could somehow travel at light speed, you could go from Earth to the Moon, a distance of about 238,000 miles in roughly 1.3 seconds. The Apollo astronauts took 3 days to make that journey. At light speed, you could cross the entire solar system, from the Sun to the orbit of Neptune, a distance of about 2.8 billion miles, in roughly 4 hours and 10 minutes. Voyager 1, humanity's most distant spacecraft, launched in 1977, has been traveling for over 40 years and has only recently left the solar system's boundary. At light speed, you could make that same journey in less than a day. But here's where Einstein enters the picture, and everything you think you know about speed starts to break down. In 1905, Albert Einstein published his theory of special relativity. The core insight was deceptively simple, but had profound implications. The speed of light is always constant, regardless of how fast you're moving. This seems impossible at first. If you're on a train moving at 100 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the ground sees the ball moving at 120 miles per hour. The speeds add up. That makes intuitive sense. But light doesn't work this way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might expect the light to move at 1.5 times light speed from the perspective of someone watching you from Earth. But it doesn't. The light moves at exactly the speed of light, about 186,000 miles per second. From your perspective and from Earth's perspective, the same speed always, for every observer, regardless of how fast they're moving. Einstein's solution to this apparent impossibility was radical. Time and space adjust to keep light speed constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still, and distances in the direction you're moving actually contract. They shrink. These aren't optical illusions or tricks of perception. They're real physical effects measured countless times in experiments. Particles in accelerators, moving at 99.9% of light speed, live much longer than identical particles at rest because time is running slower for them. Atomic clocks on airplanes tick at different rates than identical clocks on the ground. GPS satellites have to account for relativistic time dilation, or they'd give you the wrong location within minutes. This is called time dilation and length contraction, and it gets more extreme the faster you move. At 10% of light speed, the effects are small but measurable. Time runs about 0.5% slower. Distances shrink by about 0.5%. At 50% of light speed, time runs about 13% slower. Distances shrink by about 13%. At 90% of light speed, time runs about 56% slower. Distances shrink by about 56%. At 99% of light speed, time runs about 86% slower. For every year you experience, about 7 years pass on Earth. At 99.9% of light speed, time runs about 97% slower. For every year you experience, about 22 years pass on Earth. And as you get closer and closer to light speed, the effects become more and more extreme. At 99.99% of light speed, about 70 years pass on Earth for every year you experience. At 99.999%, about 224 years pass on Earth for every year you experience. The closer you get to light speed, the more time slows down from your perspective relative to everyone else. There's a mathematical term for this, called the Lorentz factor. It tells you exactly how much time dilation and length contraction you experience at any given speed. At low speeds, the Lorentz factor is close to 1, meaning almost no relativistic effects. But as you approach light speed, the Lorentz factor grows toward infinity. Time dilation and length contraction become more and more extreme without limit. So, what happens if you actually reach light speed exactly? What would the universe look like? Here's where things get truly strange. From your perspective as a traveler at light speed, time stops completely. Not slows down, stops. The Lorentz factor becomes infinite. Every second you experience, infinite time passes in the rest of the universe. Actually, you wouldn't experience any seconds at all, because time isn't passing for you. The journey from your perspective would be instantaneous. You'd leave Earth and arrive at your destination at the same moment from your own perspective, even if that destination is billions of light years away. No time would pass for you. None. you'd experience the entire journey as taking 0 seconds. From Earth's perspective, though, you'd be traveling for years or centuries or millennia, depending on the distance. They'd watch you moving at light speed, taking 4.37 years to reach Alpha Centauri, or 100,000 years to cross the Milky Way. But you wouldn't experience any of that time. The universe outside your reference frame would age, but you wouldn't. This creates a paradox of sorts. From your perspective, the journey is instantaneous. From everyone else's perspective, it takes years. Both perspectives are equally valid. There's no absolute reference frame, no universal clock that determines which perspective is correct. Time is relative, depending on your motion. But there's another effect that happens at light speed: length contraction. As you accelerate toward light speed, distances in the direction of your travel shrink from your perspective. At 99% of light speed, a distance of 100 light-years shrinks to about 14 light-years from your perspective. At 99.9%, it shrinks to about 4.5 light-years. At 99.99%, it shrinks to about 1.4 light-years. And at exactly light speed, distances shrink to 0. The entire universe, in the direction you're traveling, compresses into a single point from your perspective. Alpha Centauri, 4.37 light-years away, would be right in front of you, no distance away at all. The Andromeda Galaxy, 2.5 million light-years distant, would be right there with you. The edge of the observable universe, 93 billion light-years away, would be compressed to 0 distance. Every point in the universe, along your direction of travel, would occupy the same location from your perspective. The entire cosmos flattened into a 2-dimensional plane, perpendicular to your motion. This is what's called the headlight effect in relativity. Light and matter in front of you would be compressed into an increasingly narrow cone. At high relativistic speeds, you'd see the stars in front of you bunched together into a bright spot directly ahead, while the stars to the sides and behind would spread out. At light speed, everything in front of you would be compressed into a single, infinitely bright point. Of course, you wouldn't actually see this, because photons wouldn't be arriving at different times for you. Time isn't passing. The entire journey is instantaneous from your reference frame. So, what would you actually see? Nothing, probably, or everything at once. It's difficult to say because the scenario breaks down. You can't actually have experiences at light speed because experiences require time to pass, and time isn't passing for you. You'd leave Earth and arrive at your destination in the same instant from your own perspective, with no journey in between, like blinking and suddenly being somewhere else. But what about the universe around you? What would you actually see if you were traveling at these incredible speeds? Here's where it gets even stranger than time dilation and length contraction. The visual experience of relativistic travel would be unlike anything you've ever seen or could imagine. Light coming from objects in front of you would be blue shifted. Blue shifting happens when the source of light is moving toward you, or when you're moving toward the source. The wavelengths get compressed, squeezed together, shifted toward the blue end of the spectrum and beyond. This is the Doppler effect for light. Similar to how a siren sounds higher pitched as an ambulance approaches you, the frequency increases, the wavelength decreases. For light, increasing frequency means shifting toward blue, and beyond blue into ultraviolet, X-rays, and gamma rays. At modest speeds, blue shifting is minor. If you're driving toward a red traffic light at 60 miles per hour, the light is technically blue shifted, but the effect is so tiny that the light still looks red. Your eye can't detect the minuscule shift in wavelength. At relativistic speeds, this effect is extreme and completely changes what you see. At 50% of light speed, light from stars ahead of you is moderately blue shifted. Red stars would look orange or yellow. Yellow stars would look white or blue. The shift is noticeable, but not overwhelming. At 90% of light speed, the blue shifting becomes dramatic. Visible light from stars ahead gets shifted into ultraviolet. Infrared light gets shifted into visible light. Radio waves from cosmic sources get shifted up into microwaves and infrared. The entire electromagnetic spectrum shifts up in frequency by a factor of about 2.3. Stars ahead of you would appear much bluer and brighter than normal. The cosmic microwave background radiation, normally invisible to your eyes, would be shifted into infrared and might become detectable with infrared cameras. The universe in front would look brighter and hotter. At 99% of light speed, the blue shifting is extreme. Light from stars ahead is shifted far into ultraviolet and X-rays. What little visible light remains is pushed to the blue end of the spectrum. Most stars would be invisible to your naked eye because their light is shifted beyond what you can see, but they'd be bright in ultraviolet detectors. The cosmic microwave background would be shifted into visible light. You'd see a faint glow filling the sky ahead, the afterglow of the Big Bang now visible because you're moving so fast that its wavelength is compressed into the visible spectrum. Normally, this background radiation has a temperature of about 2.7 Kelvin, just above absolute zero. At 99% of light speed, it would be blue shifted to appear as though it has a temperature of about 19 Kelvin, still cold, but significantly warmer from your perspective. At 99.9% of light speed, the cosmic microwave background would be blue shifted to about 60 Kelvin. At 99.99%, about 190 Kelvin. At 99.999%, about 600 Kelvin, hot enough to glow visibly. You'd see the relic radiation from the Big Bang as a bright glow in front of you, and starlight would be shifted into hard X-rays and gamma rays. Every photon coming toward you, regardless of its original wavelength, gets shifted to higher and higher energies the faster you move. At light speed, the blue shifting becomes infinite. Every photon coming toward you would be blue shifted to infinite energy. The cosmic microwave background radiation, normally a faint signal from the Big Bang, barely warmer than empty space, would be shifted into high-energy gamma rays. Its effective temperature from your perspective would be infinite. Starlight would be shifted far beyond gamma rays into energies we don't even have names for. Photons that left their source as gentle visible light would arrive as radiation so energetic it could tear apart atoms. The universe in front of you would become an infinitely energetic radiation field, a wall of radiation so intense that it's hard to imagine. Not just bright, but infinitely energetic. And this radiation would be lethal. Even at 99.99% of light speed, before you reach the infinite limit, the blue-shifted cosmic background radiation and starlight would cook anything in front of you. Your spacecraft would need shielding not just against particle impacts, but against radiation, thick layers of matter to absorb gamma rays. But how do you shield against infinitely energetic photons? You can't. At exactly light speed, the radiation is infinite, and no shielding is thick enough. Another reason why light-speed travel is impossible. The universe ahead would literally become a wall of infinite energy. Simultaneously, light from behind you would be redshifted. Redshifting is the opposite of blue shifting. Wavelengths get stretched, lengthened, shifted toward the red end of the spectrum and beyond into infrared, microwaves, and radio waves. The frequency decreases, the energy decreases. At 99% of light speed, visible light from stars behind you gets shifted into infrared. Blue stars would look red or orange. Red stars would disappear into infrared, invisible to your naked eye. At 99.9%, most visible light from behind is shifted into deep infrared or microwaves. The stars behind you would disappear from view, their light stretched into wavelengths your eyes can't see. At 99.99%, even infrared gets shifted into radio waves. The stars behind you would be emitting radio waves from your perspective, completely invisible without a radio telescope, and at light speed, the redshifting becomes infinite. Every photon from behind you would be redshifted to infinite wavelength, which means zero frequency, which means zero energy. Light from behind you would effectively disappear. Not just become invisible, but cease to carry energy. You'd see nothing behind you. Complete darkness in your rearward direction. The universe would vanish. So from your perspective, at light speed, if you could somehow perceive anything, the universe ahead would be an infinitely bright, infinitely energetic point compressed into a cone directly in front of you. And the universe behind would be complete darkness, nothing, absence of light and energy. Everything compressed into a single forward-facing direction. The entire cosmos reduced to a point of infinite radiation ahead and void behind. Not exactly a pleasant journey. Not survivable by any stretch. Even at fractions of light speed, well below 100%, the radiation environment would be harsh. At 99.99% of light speed, you'd need massive shielding just to protect against the blue-shifted cosmic background radiation, which would be hitting you with the energy of X-rays and gamma rays. And we haven't even talked about the visual distortion yet. There's another effect called relativistic beaming, or the searchlight effect. As you move at relativistic speeds, light from the sides appears to shift forward. Imagine you're stationary and you look around. You see stars in all directions, ahead, behind, to the sides, above, below, a sphere of stars surrounding you. But if you're moving at relativistic speed, the stars to your sides appear to shift forward into your direction of motion. At 99% of light speed, stars that were 90 degrees to your side, directly perpendicular to your motion, appear to be about 10 degrees off your forward direction. They've shifted dramatically toward the front. At 99.9%, they appear to be about 4 degrees off center. At 99.99%, about 1.4 degrees. The faster you move, the more the stars bunch together into a narrow cone in front of you. At light speed, all the stars, the entire universe, would appear to be concentrated into a single point directly ahead. You'd see nothing to the sides, nothing behind, everything compressed into a forward direction. This is called the headlight effect, because it's like driving at night with your headlights on. The light is concentrated in a narrow beam ahead, while the sides and rear are dark. At relativistic speeds, the universe looks like that. A bright spot ahead, darkness everywhere else. And it gets worse. Because of length contraction, the universe in your direction of travel is compressed. Distances shrink. At 99.9% of light speed, a distance of 10 light-years shrinks to about 0.45 light-years from your perspective. At 99.99%, it shrinks to about 0.14 light years. At light speed, it shrinks to zero. So not only does the universe visually compress into a point ahead of you, but the actual spatial distance compresses too. Stars that are separated by light years would appear right next to each other from your perspective. The space between them squeezed down to nothing. You'd be traveling through a universe that's spatially flattened in your direction of motion. Like looking at a three-dimensional scene compressed into a flat plane. Depth disappears. Everything along your line of sight occupies the same location. You couldn't distinguish near from far because there is no near or far. Everything is here, at zero distance, compressed into the present moment. And then there's the question of what happens to time itself from your perspective. We've talked about time dilation. From Earth's perspective, how your clock runs slow compared to theirs. But from your perspective, time is running normally for you. Your heartbeat feels normal. Your thoughts occur at normal speed. You experience 1 second per second as always. But when you look out at the universe, you see Earth's time running fast. At 99.9% of light speed, for every second you experience, about 22 seconds pass on Earth from your observation. You'd see Earth spinning 22 times faster than normal. Days would pass in just over an hour from your perspective. The sun would rise and set 22 times while you experience a single day. Weeks would pass in about 8 hours. Months in about a day. If you looked at Earth through a telescope, you'd see seasons changing rapidly, clouds moving at high speed, cities growing and changing before your eyes. Civilization evolving in fast forward. At 99.99%, Earth's time runs 70 times faster from your perspective. A year on Earth would pass in about 5 days from your perspective. You'd watch decades unfold in months, centuries in years. At 99.999%, 1,000 years on Earth would pass in about 4.5 years of your time. You'd watch human history unfold like a time-lapse video. Empires rising and falling. Technology advancing from primitive to futuristic. The entire arc of civilizations compressed into a viewable time frame. And at exactly light speed, you'd see Earth's time running infinitely fast. The entire future of Earth, from your departure to the heat death of the universe, would occur in zero time from your perspective. You'd witness the end of everything instantaneously. Not that you'd actually experience this, because at light speed, you don't experience time. The journey is instantaneous from your perspective. No time passes, so you don't see anything happen. You leave and arrive in the same moment. But conceptually, from a light-speed reference frame, the entire timeline of the universe is compressed into a single moment. Past, present, and future exist simultaneously. Time, as a dimension, ceases to have meaning. This is what photons experience, if they could be said to experience anything. A photon, emitted from the sun, travels for 8 minutes from Earth's perspective. But, from the photon's perspective, no time passes. It's created in the sun's core and absorbed in your eye at the same instant. The 8-minute journey that we observe doesn't exist for the photon. It exists in a timeless state. This is the reality of light speed. Time stops. Space compresses to zero. The universe becomes a point of infinite energy. You exist outside the normal flow of causality, in a realm where the concepts of before and after don't apply. It's not travel in any meaningful sense. It's a transition from one state to another with no journey in between. Now let's talk about the practical problems of actually accelerating to light speed. The energy required. This is where the dream of light-speed travel crashes into the hard reality of physics. Einstein's most famous equation is E equals mc squared. Energy equals mass times the speed of light squared. This tells us that mass and energy are equivalent, interchangeable. It's not just a clever mathematical relationship, it's a fundamental truth about the universe. Mass is concentrated energy. Energy can be converted into mass. They're two forms of the same thing. When you heat water, you're adding energy to it, and technically, you're increasing its mass, though by an amount far too small to measure. When atoms split in nuclear reactions, they release energy, and the products have slightly less mass than the original atom. That missing mass was converted to energy. E equals mc squared tells us the exchange rate. But there's another implication buried in this equation that becomes critical at high speeds. As you accelerate an object, you're adding energy to it. You're doing work on it, pumping energy into its motion. And because mass and energy are equivalent, adding energy increases the object's mass. Not its rest mass, the mass it has when sitting still, but its relativistic mass, the mass it has when moving. At low speeds, this effect is negligible, completely unmeasurable. Accelerating a car from 0 to 60 miles per hour increases its mass by about 1/10,000,000,000%. You'd need the most sensitive instruments ever built to detect such a tiny change. For all practical purposes, the car's mass stays the same. But at relativistic speeds, speeds that are a significant fraction of the speed of light, the effect becomes noticeable, then significant, then dramatic, then overwhelming. As you accelerate toward light speed, your mass increases, not just a little, but substantially. The closer you get to light speed, the more your mass increases. And increasing mass means it takes more force to accelerate further, which means it takes more energy to achieve the same change in velocity. At 99% of light speed, your mass is about 7 times your rest mass. If you normally weigh 150 pounds, at 99% of light speed, you'd effectively weigh over 1,000 pounds from the perspective of someone watching you. Your actual rest mass hasn't changed. You're still made of the same atoms with the same rest mass, but your energy of motion has added so much relativistic mass that you now have 7 times the inertia you had at rest. Accelerating you further takes 7 times the force it would have taken when you were at rest. At 99.9% of light speed, your mass is about 22 times your rest mass. At 99.99%, it's about 70 times your rest mass. At 99.999%, it's about 224 times your rest mass. The pattern continues. Each additional 9 you add to the decimal brings another 10-fold increase in relativistic mass. As you approach light speed, your mass approaches infinity. Not approaches some large number, approaches actual infinity. The Lorentz factor, which determines how much your mass increases, grows without bound as your velocity approaches light speed. At 99.999% of light speed, your mass would be about 7,000 times your rest mass. At 99.99999%, it would be about 70,000 times your rest mass. There's no limit to how massive you become as you get closer to light speed. And accelerating infinite mass requires infinite energy. No matter how much energy you apply, you can never quite reach light speed because you're pushing against an ever-increasing mass that grows toward infinity. The universe doesn't have infinite energy available, so nothing with mass can reach light speed. It's not a technological limitation that we might overcome with better engines or more fuel. It's a fundamental barrier written into the structure of space-time itself. This is why nothing with mass can actually reach light speed. It would take infinite energy to get there, and infinite energy doesn't exist. The universe prevents you from reaching light speed by making it require resources that aren't available. It's a hard limit, an absolute barrier. Let's put some numbers to this to really understand the scale of the challenge. Suppose you want to accelerate a spacecraft with a mass of 1,000 kilograms to 99% of light speed. 1,000 kilograms is about the mass of a small car, or a very minimal spacecraft with barely any equipment or supplies. No life support for humans, no comfortable living quarters, just a bare minimum probe. The kinetic energy required to accelerate this 1,000 kilogram spacecraft to 99% of light speed would be about 5.5 times 10 to the 20th joules. That's 550 quintillion joules. To put that in perspective, that's about the total energy output of the Sun for 1 second. Our Sun produces about 3.8 times 10 to the 26th watts of power. In 1 second, it outputs 3.8 times 10 to the 26 joules. So, accelerating our tiny 1,000 kilogram spacecraft to 99% of light speed requires energy equivalent to what the Sun produces in about 1.7 seconds. The Sun, the massive fusion reactor at the center of our solar system that powers all life on Earth. That outputs more energy in 1 second than all human civilization has used in our entire history. You need more than a second of its total output just to accelerate a 1,000 kilogram spacecraft to 99% of light speed. Let's compare this to human energy consumption. Global human energy consumption is about 600 exajoules per year. That's 6 times 10 to the 20th joules annually. Our tiny spacecraft's energy requirement, 5.5 times 10 to the 20th joules, is roughly equal to all energy used by all humans on Earth for an entire year. All the electricity, all the fuel for cars and planes, all the heating and cooling, all the industrial processes, everything. That's how much energy you need for one small spacecraft to reach 99% of light speed. And we're talking about barely getting to 99%, not even 99.9%. To reach 99.9% of light speed would require about 19.5 times 10 to the 20th joules. About 3 times more energy. That's about 3 years of total global human energy consumption. To reach 99.99% would require about 62 times 10 to the 20th joules. About 10 years of global energy consumption. The energy requirements grow exponentially as you approach light speed. Each additional 9 you add to your velocity requires roughly 3 times more energy than the previous level. By the time you reach 99.9999% of light speed, you're looking at energy requirements equivalent to centuries of human civilization's total energy output for one small spacecraft. And we're talking about a tiny probe, just 1,000 kilograms. A spacecraft large enough to carry humans with life support, food, water, air, radiation shielding, living quarters, and propulsion systems would have a mass far greater. The International Space Station has a mass of about 420,000 kilograms. That's 420 times more massive than our hypothetical 1,000 kilogram probe. Accelerating something the size of the ISS to 99% of light speed would require energy equivalent to the sun's output for about 12 minutes, or about 420 years of total human energy consumption. To put it another way, if we could somehow capture all the energy humanity produces and store it perfectly with no losses, it would take us over 4 centuries to gather enough energy to accelerate one ISS-sized spacecraft to 99% of light speed. And that's assuming perfect efficiency, which is impossible. Real engines have losses. Real systems waste energy as heat. You'd need far more than the theoretical minimum. The challenge becomes even more daunting when you account for the fuel itself. Where would that energy come from? You need to carry it with you because there's nothing to push against in space. No air for a jet engine. No road for wheels. You can't just burn fuel and push against the ground. You have to expel mass backward at high speed, and the reaction pushes you forward. That's how rockets work. They carry both fuel and oxidizer, burn them together, and expel the exhaust at high velocity. The faster you can expel the exhaust, the more efficient your rocket is. Chemical rockets expel exhaust at a few miles per second, about 1.9 to 2.8 miles per second for the best chemical rockets. That's fast by everyday standards, but tiny compared to light speed. To get better efficiency, you need higher exhaust velocities. Nuclear thermal rockets could potentially expel exhaust at 5 to 6 miles per second. Nuclear, electric, or ion drives could reach 31 to 62 miles per second, or even higher. But even the best theoretical ion drives are still expelling matter at tiny fractions of light speed. The most efficient energy source we know of is matter-antimatter annihilation. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to E equals mc squared, a perfect conversion. No other process is more efficient. Nuclear fusion, which powers the sun and hydrogen bombs, converts about 0.7% of the mass into energy, less than 1%. The rest remains as matter, just rearranged into different elements. Matter-antimatter annihilation converts 100% of the mass into energy, mostly in the form of gamma rays and other high-energy particles. This is the absolute limit of energy efficiency allowed by physics. If you could build a matter-antimatter rocket engine, it would be the most efficient rocket theoretically possible. You could potentially expel the annihilation products at speeds approaching light speed, giving you maximum exhaust velocity. But even with this perfect efficiency, you still need enormous amounts of fuel. To accelerate a 1,000 kilogram spacecraft to 99% of light speed using matter-antimatter annihilation, you'd need about 7,000 kilograms of fuel. Half matter, half antimatter. 3,500 kilograms of matter and 3,500 kilograms of antimatter. When they annihilate, they produce 7,000 kilograms worth of energy, which is used to accelerate your spacecraft. So your total spacecraft mass is now 8,000 kilograms. 1,000 kilograms of payload and 7,000 kilograms of fuel. 7 times more fuel than payload. But wait, there's a problem. You also need to accelerate that 7,000 kilograms of fuel to 99% of light speed. The fuel doesn't start at 99% of light speed. It starts at rest along with your spacecraft, which means you need more fuel to accelerate the fuel. This is called the tyranny of the rocket equation. Discovered by Konstantin Tsiolkovsky in 1897. The more fuel you need, the more mass you have to accelerate, which means you need even more fuel, which increases the mass further, which requires even more fuel. It's a vicious cycle. The final calculation, accounting for the need to accelerate the fuel itself, shows you'd actually need about 10,000 kilograms of matter-antimatter fuel to accelerate a 1,000 kilogram payload to 99% of light speed. 10 times the payload mass in the most efficient fuel theoretically possible. And that's just to accelerate. If you want to decelerate when you arrive at your destination, you need to carry even more fuel for the deceleration burn, which doubles your fuel requirement. Now you need 20,000 kilograms of fuel for a round trip with acceleration and deceleration. 20 times your payload mass. Your spacecraft is now 21,000 kilograms total, 95% fuel, 5% payload. And we're still talking about reaching only 99% of light speed, not 99.9 or 99.99. To reach higher fractions of light speed, the fuel requirements grow exponentially. By the time you want to reach 99.99%, you'd need hundreds of thousands of kilograms of fuel for a 1,000 kilogram payload. The spacecraft becomes almost entirely fuel with a tiny payload. And here's the real problem. We don't have antimatter. We can't make it in useful quantities. We can produce it in particle accelerators, a few atoms at a time, at costs of trillions of dollars per gram. The total amount of antimatter ever produced by humanity is measured in nanograms, billionths of a gram. If we could somehow collect all the antimatter ever made in all the particle accelerators ever built, it would be less than a microgram. Far less. We'd need kilograms, millions of times more than has ever existed. And even if we could produce it, we have no way to store it. Antimatter annihilates instantly on contact with normal matter. Touch a container made of matter, and the antimatter destroys the container and itself in a burst of gamma rays. You'd need some kind of magnetic bottle that holds the antimatter suspended in a vacuum, never touching the walls. We can do this for individual atoms, in laboratory conditions for short periods. But storing kilograms of antimatter for months or years during a space journey, completely beyond current technology. One power failure, one small malfunction, and the antimatter touches the walls and your entire fuel supply annihilates instantly. The energy release would be equivalent to a massive thermonuclear explosion. You don't just lose your fuel, you vaporize your spacecraft and everything nearby. So matter-antimatter rockets are pure theoretical speculation at this point. We have the equations, we understand the physics, but we have no practical way to build one. And even if we solve the antimatter production and storage problems, there are still other challenges. At 99% of light speed, interstellar hydrogen atoms would hit your spacecraft with enormous energy. Space isn't completely empty. There's about 1 hydrogen atom per cubic centimeter in interstellar space on average. That sounds sparse, and it is by everyday standards. But when you're moving at 99% of light speed, you're sweeping through an enormous volume of space every second. At 99% of light speed, you cover about 184,000 miles per second. That's about 184,000 miles per second. Every second, your spacecraft sweeps through a cylinder of space about 184,000 miles long and as wide as your spacecraft. If your spacecraft has a cross-sectional area of 10 square meters, you're sweeping through about 3 billion cubic meters of space per second. At 1 hydrogen atom per cubic centimeter, that's about 3 times 10 to the 15th atoms per second hitting your spacecraft. 3 quadrillion hydrogen atoms every second. each one moving at 99% of light speed relative to you. The kinetic energy of a single hydrogen atom at 99% of light speed is about 1.2 times 10 to the minus 9 joules. That might sound tiny, but multiply by 3 quadrillion atoms per second and you're absorbing about 3.6 million joules per second. 3.6 megawatts of power continuously hitting your spacecraft. That's like having a beam from a powerful industrial laser constantly focused on you. Your spacecraft would heat up. You'd need cooling systems, radiators to dump the heat into space, and you'd need shielding to protect against the particle impacts. Each hydrogen atom hits with the energy of a particle in a high-energy physics accelerator. At 99% of light speed, each proton carries about 7 giga-electron volts of energy. That's high-energy cosmic ray territory. Over time, this radiation would damage your spacecraft structure. It would create defects in the hull, weaken materials, potentially cause equipment failures. You'd need thick shielding, meters of material to absorb the impacts. But shielding adds mass. More mass means more fuel needed, which adds more mass. The rocket equation strikes again. At higher fractions of light speed, the problem gets exponentially worse. At 99.9%, each hydrogen atom hits with about 22 giga-electron volts of energy. At 99.99%, about 70 giga-electron volts. You'd need tens of meters of shielding to protect against this radiation. The spacecraft mass grows to absurd levels. Maybe you could use magnetic fields to deflect the incoming charged particles. A powerful magnetic field around your spacecraft could push protons and other charged particles away before they hit. But generating magnetic fields strong enough to deflect giga-electron volt energy particles requires enormous amounts of power, and the magnetic field itself adds mass in the form of superconducting coils and power systems. There's no easy solution. Every approach adds mass, which requires more fuel, which adds more mass, and the cycle continues. Some physicists have proposed using the incoming hydrogen as fuel. A ramjet that scoops up interstellar hydrogen and fuses it for propulsion. The Bussard ramjet, proposed by Robert Bussard in 1960. The idea is elegant. You don't carry fuel. You collect it as you go from the interstellar medium. A huge magnetic scoop, maybe thousands of miles across, funnels hydrogen into your fusion reactor. You fuse the hydrogen, extracting energy, and expel the products for thrust. As long as you're moving through space with hydrogen available, you have unlimited fuel. You could accelerate continuously, potentially reaching very high fractions of light speed. The problem is that the drag from scooping up the hydrogen might exceed the thrust from fusing it. You'd be pushing through a thin soup of hydrogen, and collecting it creates resistance. The faster you go, the more drag you encounter. Calculations suggest that a Bussard ramjet might not be able to accelerate beyond a certain speed because the drag equals the thrust. You'd asymptotically approach a terminal velocity, unable to go faster. And building a magnetic scoop thousands of miles across is engineering far beyond anything we can currently imagine. The mass of the scoop, the power required to run it, the structural integrity needed to hold it together while moving at relativistic speeds, all present enormous challenges. It's theoretically possible within known physics, but practically it might be impossible. Another idea is the laser sail. Instead of carrying fuel, you're pushed by a powerful laser beam from Earth or from solar orbit. The spacecraft carries a large, lightweight sail made of reflective material. A laser on Earth or in space focuses on the sail and pushes it with light pressure. Photons carry momentum, and when they reflect off the sail, they transfer that momentum. The spacecraft accelerates. The advantage is that you don't carry fuel. All the energy comes from the laser station, which can be massive and doesn't need to move. You could potentially build enormous laser arrays in orbit around the Sun, powered by solar energy, and use them to push spacecraft to high speeds. The spacecraft itself is just a sail and a tiny payload, very low mass. The downside is that you can't decelerate unless there's another laser at your destination to slow you down, which there won't be for interstellar journeys. You'd arrive at high speed and fly right past your target. Unless you carry a small amount of fuel for deceleration, which brings back the mass problem, or unless your sail can somehow reflect light from the destination star to slow down, but the geometry of that is extremely difficult. Still, laser sails might be the most practical approach for sending small probes to nearby stars. The Breakthrough Starshot project, funded by Yuri Milner and supported by scientists like Stephen Hawking and Freeman Dyson before their deaths, proposes exactly this. Send thousands of tiny spacecraft, each weighing just a few grams, equipped with light sails. Accelerate them to 20% of light speed using a powerful Earth-based laser array. The journey to Alpha Centauri would take about 20 years. The probes would fly past, taking photos and measurements, and transmit data back to Earth using tiny lasers. 20% of light speed is far less than 99%, but it's still fast enough to make interstellar travel possible within a human lifetime from Earth's perspective. And the energy requirements, while enormous, are at least imaginable. You're accelerating grams instead of kilograms or tons, and you're only reaching 20% instead of 99%. The energy needed is vastly less. Still, a huge engineering challenge, but possibly achievable with future technology. This might be our only realistic path to interstellar travel in the foreseeable future. Small, fast probes rather than large, crude starships. Robots instead of humans. Flyby missions instead of landings and colonies. It's not the grand vision of science fiction, but it's what physics and engineering allow. And there's an even more fundamental problem. Let's say you somehow solve all of these issues. You build a spacecraft, you generate the fuel, you accelerate to 99.9% of light speed, and you start your journey to Alpha Centauri. From Earth's perspective, the journey takes about 4.4 years. They watch you depart, travel for 4.4 years at constant velocity, and arrive. But from your perspective, time is dilated by a factor of about 22. For every year you experience, 22 years pass on Earth. So, the 4.4-year journey from Earth's perspective takes only about 0.2 years from your perspective, about 2.4 months, less than a quarter of a year. You leave Earth on January 1st, experience 2.5 months of travel time, and arrive at Alpha Centauri in mid-March from your perspective. But when you arrive, Earth's calendar reads late April, 4 years later. Everyone you knew has aged 4.4 years. Your best friend, who was 30 when you left, is now 34. Your children, if you had them, are 4 years older. A child who was 10 when you left is now 14, going through puberty, becoming a teenager while you experienced less than 3 months. If you had a spouse who stayed behind, they've lived 4 years of life without you, 4 years of birthdays and holidays and daily experiences. 4 years of changes and growth and aging. And you've experienced 10 weeks. The asymmetry is profound and strange. If you turn around and come back, another 4.4 years pass on Earth from their perspective, while you experience another 2.5 months. The total round trip from your perspective takes about 5 months. You age 5 months. You experience 5 months of memories and experiences. But Earth has aged 8.8 years, almost 9 years. Your twin, who was 30 when you left, is now 38, nearly 39. Your children who were 10 are now 18 or 19. Adults, graduated from high school, maybe in college or starting careers. Your spouse has lived nearly a decade without you, probably moved on, built a new life. The world has changed. Technology has advanced. Culture has shifted. Politics have evolved. New movies have come out. New music, new fashions, new slang. 9 years of human progress compressed into what felt like 5 months for you. This is the twin paradox, one of the most famous thought experiments in relativity. If you have an identical twin who stays on Earth while you make this journey, when you return, your twin will be about 8.5 years older than you. Biologically, physically, actually older. More grey hair? Maybe. More wrinkles. Closer to middle age, while you're still in your early 30s or wherever you started. The paradox isn't that this happens. The math is clear and the effect is real. The paradox is that it seems like it should be symmetrical. From your perspective on the spaceship, Earth is moving away from you at 99.9% of light speed. So shouldn't time on Earth be running slow from your perspective? Shouldn't your twin age slower than you, not faster? The resolution is that the situation isn't symmetrical. You're the one who accelerated. You're the one who turned around and came back. You felt forces during acceleration and deceleration. Your twin didn't. The twin on Earth remained in an inertial reference frame, not accelerating, just moving with Earth's rotation and orbit, which are negligible compared to relativistic speeds. You were in a non-inertial reference frame, accelerating significantly, feeling forces. Special relativity only applies to inertial reference frames. When you account for the acceleration phases using general relativity, which handles non-inertial frames, the asymmetry resolves. Your twin ages more because you accelerated, not them. This isn't theoretical speculation. This actually happens. Astronauts on the International Space Station age slightly slower than people on Earth because they're moving faster in orbit. The ISS orbits at about 17,500 miles per hour. That's fast by everyday standards, but tiny compared to light speed. Only about 0.0026% of light speed. At that speed, time dilation is minuscule. An astronaut who spends 6 months on the ISS ages about 0.005 seconds less than someone who stayed on Earth. 5/1000ths of a second. Barely measurable, but real. Atomic clocks are precise enough to detect it, and the measurements match Einstein's predictions exactly. At truly relativistic speeds, the effect is dramatic. You could travel to a star 100 light-years away at 99.99% of light speed. From Earth's perspective, the journey takes about 100 years. From your perspective, time is dilated by a factor of about 70, so you experience only about 1.4 years of travel, less than a year and a half. You leave Earth, spend a year and a half traveling, and arrive at a star 100 light-years away. But Earth is 100 years older. Everyone you knew is dead. Not just your friends and family, but everyone from your generation. Your great-grandchildren are now old or dead themselves. Civilization has progressed a century. Technology has advanced beyond recognition. History has moved on. And if you come back, another 100 years pass on Earth while you experience another year and a half. You'd return to Earth 200 years after you left, 2 centuries in the future. Your species has evolved, culturally, if not biologically. The world you left is ancient history. You'd be a living fossil, a person from the past emerging into a future you can't comprehend. This is the price of relativistic travel. You can cover vast distances in short, subjective time, but you're traveling into Earth's future. There's no going back to your own time, no way to return to the era you left. You become a time traveler, leaping forward in Earth's timeline while experiencing only a brief journey yourself. Some science fiction stories embrace this. The crew of a relativistic starship accepts that they're leaving their era behind. They know they'll arrive at their destination in their own future, emerging into a time where everyone they knew is long gone. It's a one-way trip in time as well as space. A voyage to a new world and a new era simultaneously. But it raises profound psychological and emotional questions. Would people volunteer for such missions? Would you accept a journey knowing everyone you love will age decades or centuries while you're gone? Knowing you can never return to your own time, that you're abandoning your entire context, your culture, your generation, everything familiar? Some might. Explorers, pioneers, people seeking a new start, people willing to sacrifice their connection to their own time for the chance to see new worlds and new futures. People who feel unattached to their current era, who have no strong ties, who want to escape, or people driven by curiosity so strong they're willing to pay any price to see what lies beyond. But it would be a small fraction of humanity. Most people wouldn't make that trade. Most people value their connections, their relationships, their place in their own time. They want to be part of their society's unfolding story, not skip to the end. They want to age alongside their loved ones, not leave them behind to age alone. The relational cost of relativistic travel might be even more prohibitive than the energy cost. Even if we could build the ships, even if we could generate the fuel, would anyone actually want to go? And there's another consideration. What about communication? If you're traveling to Alpha Centauri at 99.9% of light speed and you want to send a message back to Earth, how long does it take? From Earth's perspective, you're 4.4 light years away, so the message takes 4.4 years to arrive, traveling at light speed. But you've only been traveling for a few months from your own perspective. The message you send arrives on Earth years after you left from their timeline, but only weeks after you left from your timeline. Time becomes desynchronized. Conversations become impossible. You send a message, Earth receives it years later. They send a reply. You receive it years after that, from their perspective. By the time you receive their response to your first message, decades might have passed on Earth. The people who sent the reply might be old or dead. You're not having a conversation. You're exchanging messages across time as well as space. This is already true to a small extent with spacecraft in our solar system. A message to Mars takes between 4 and 24 minutes, one way, depending on the positions of the planets. A conversation with someone on Mars would have a delay of 8 to 48 minutes between question and answer. Awkward, but manageable. A message to Voyager, one takes about 22 hours one way. You send a command, wait 44 hours, and get a response. No real-time conversation, just delayed exchanges. But interstellar distances are far worse. Alpha Centauri is 4.4 years away at light speed. Any message takes nearly 9 years round trip. You can't have a conversation across interstellar distances. You can only send letters that take years to deliver and years to get responses. And with relativistic time dilation, the disconnect becomes even stranger. You might send a message from your perspective early in the journey, but from Earth's perspective, you sent it years into your flight. The timelines don't match up. Synchronizing events between your reference frame and Earth's becomes a logistical nightmare. This is one reason why interstellar colonization, if it ever happens, would probably mean permanent separation. Once a colony ship leaves for another star, it's effectively gone. They might send messages back, reports of their progress and eventual arrival, but meaningful communication is impossible. They're on their own, isolated by distance and time from the civilization that sent them. Each colony would develop independently, diverging culturally and probably eventually biologically from Earth and from each other. Over thousands or millions of years, humanity could become multiple species scattered across the galaxy, each adapted to their own world, each following their own evolutionary path, connected only by distant origin, not by ongoing contact, a diaspora across space and time. There's another strange consequence of light-speed travel: relativity of simultaneity. Events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. Imagine you're on Earth and two events happen at the same time, one on the East Coast and one on the West Coast. You'd say they happened simultaneously. But someone traveling at relativistic speed past Earth would say one event happened before the other. Not because of signal delays or light travel time, but because the actual ordering of events in time depends on your reference frame. At light speed, this effect becomes extreme. The concept of now, of what's happening right now across the universe, becomes meaningless. There's no universal present moment. Different observers have completely different presents. An observer at light speed would have a present moment that's infinitely far in the future for some parts of the universe, and infinitely far in the past for others, depending on direction. The very structure of time becomes warped. This is one reason why light speed is a barrier. If you could exceed light speed, you could arrive before you left from certain reference frames. Causality would break down. Effects could precede causes. The universe would become paradoxical. This is why special relativity predicts that nothing with mass can reach or exceed light speed. It's not a technological limitation, it's a fundamental law of physics. Only things without mass, like photons, can travel at light speed, and photons don't experience time. From a photon's perspective, if photons had perspectives, the journey from the Sun to Earth is instantaneous. The photon is created in the Sun's core and absorbed in your eye at the same instant from its own reference frame. The 8 minutes that pass from our perspective don't pass for the photon. It exists in a timeless state, created and destroyed in the same moment. This is what you'd experience at light speed. No journey, no passage of time, instantaneous transport from origin to destination. But only if you had no mass, which you do. So light speed remains forever out of reach for anything physical. Still, physicists have speculated about theoretical ways around the light speed barrier. Not by actually traveling faster than light through space, but by manipulating space-time itself. Warp drives, for instance. The Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994, is one of the most famous theoretical methods of faster-than-light travel. The idea is beautifully clever. Instead of moving your spacecraft through space at faster-than-light speed, which relativity forbids, you move space itself around your spacecraft. You compress space in front of your spacecraft, making the distance shorter. And you expand space behind your spacecraft, pushing yourself away from where you were. The spacecraft sits inside a bubble of flat space-time, not moving at all relative to the space immediately around it. But that bubble of space is moving through the larger space-time, carrying the spacecraft along like a surfer on a wave. The surfer isn't swimming faster than the wave. They're being carried by the wave itself, riding its motion. Similarly, an Alcubierre drive would create a wave in space-time that carries your spacecraft. From your perspective, inside the bubble, you're not moving at all. You're sitting still in flat space. No acceleration, no forces, no G-forces pushing you back in your seat. Space outside the bubble is doing all the moving. This avoids all the relativistic effects we've been discussing. No time dilation, because you're not moving relative to local space. No length contraction, because the space inside your bubble remains flat and normal. No blue shifting or red shifting of light, because you're stationary relative to your immediate surroundings. No mass increase, because you're not accelerating. The space inside your bubble travels as a unit, carrying you along without you experiencing any of the physics that makes light-speed travel impossible. It's a genuine loophole in relativity, if it works. Einstein's equations don't forbid space itself from moving faster than light. They forbid matter and energy from moving faster than light through space. But space can do whatever it wants. In fact, during cosmic inflation, in the first fraction of a second after the Big Bang, space expanded faster than light. Regions of the universe separated faster than light could travel between them because space itself was expanding. The galaxies weren't moving through space. Space was expanding and carrying them apart. This is still happening today. Distant galaxies are receding from us faster than light because the space between us and them is expanding. We can't ever reach them. Not because they're moving away too fast, but because space is growing between us faster than we can cross it. So, faster than light motion of space is allowed by general relativity. The Alcubierre drive tries to exploit this. Create a bubble where space contracts in front and expands behind, and ride that wave to your destination. On paper, the mathematics work. Alcubierre wrote down a solution to Einstein's field equations that describes exactly this scenario. A space-time metric where a bubble of space moves faster than light, while the interior remains flat and stationary. The equations don't forbid it, but there are enormous practical problems. First, and most fundamentally, creating the warp bubble requires exotic matter with negative energy density, not antimatter, which has positive energy density, just like normal matter. Exotic matter with genuinely negative energy. Mass that weighs less than nothing. Energy that has a negative value. We've never observed such matter in nature. It might not exist at all. Quantum field theory suggests that negative energy densities might be possible in very specific, limited circumstances. The Casimir effect, where two uncharged metal plates in a vacuum attract each other due to quantum fluctuations, involves negative energy density in the region between the plates. But the effect is tiny, measurable only at microscopic scales. And it's not clear if you can extract that negative energy or use it to warp spacetime on macroscopic scales. Creating enough exotic matter to warp space around a spacecraft is purely speculative. We have no idea if it's possible. We have no mechanism to produce it, even if it exists. It might be fundamentally impossible, a solution to the equations that nature doesn't allow in practice. Second, the energy requirements are staggering beyond comprehension. Alcubierre's original calculations suggested you'd need more energy than exists in the entire observable universe to create the warp bubble. The mass energy of all the stars, all the galaxies, all the matter and dark matter in the observable cosmos wouldn't be enough. An impossible requirement. Later, physicists tried to refine the calculations, finding ways to reduce the energy needed. In 1999, Chris van den Broek proposed a modified Alcubierre metric that reduced the energy requirement dramatically, down to about the mass of Jupiter. Still an enormous amount, but at least it's a finite quantity that exists somewhere in the universe, rather than more than everything. More recent work has suggested ways to reduce it further, potentially down to the mass of a large spacecraft or even smaller. But we're still talking about concentrating enormous amounts of energy in very specific configurations of exotic matter. Even if the requirement is only the mass energy of a spacecraft rather than a planet, you still need to convert that mass entirely into exotic negative energy density matter and arrange it in exactly the right geometry. We have no technology even remotely approaching this capability. Third, there are causality problems that might make warp drives impossible. Some analyses suggest that Alcubierre drives could create closed, time-like curves. These are paths through space-time that loop back to their own past. Time travel to the past. If you could create a warp bubble, you might be able to use it to arrive at your destination before you left, from certain reference frames. This creates paradoxes. The grandfather paradox, where you go back in time and prevent your own birth, so you were never born to go back in time. Most physicists believe the universe has built-in protections against causality violations. Something, perhaps quantum mechanics or an unknown aspect of physics, prevents closed time-like curves from forming. Whenever you try to create one, something happens to stop you. The exotic matter destabilizes, the warp bubble collapses, something. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel to the past and the paradoxes it would create. We don't know if this is true, but it's a reasonable guess based on the fact that we never see causality violations in nature. If warp drives allow time travel, and time travel is impossible, then warp drives must be impossible too. Fourth, and perhaps most problematically, you can't control the warp bubble from inside it. Once the bubble is created and moving, you can't steer it or turn it off from within. Why? Because signals inside the bubble can't propagate to the boundary faster than light. The boundary of the bubble is moving faster than light relative to the space outside. Any signal you send toward the boundary, even a light-speed signal, can't catch up. It's like trying to swim to shore when the current is faster than you can swim. You'll never reach it. So, once you're inside a moving warp bubble, you're trapped. You can't communicate with the outside. You can't adjust the bubble's trajectory. You can't stop it. You'd need external mechanisms to create the bubble, guide it, and collapse it when you reach your destination. Essentially, you need infrastructure at both your starting point and your destination. A network of warp generators that create bubbles and steer them between stations. You couldn't explore freely. You could only travel between established routes with infrastructure at both ends. And you'd have no control during the journey. You'd be a passenger in a bubble, hopefully aimed correctly at your destination, unable to do anything if something went wrong. Despite all these challenges, the Alcubierre drive remains an interesting theoretical concept. It shows that faster-than-light travel might not be completely forbidden by the laws of physics, just incredibly difficult and probably impossible with anything resembling current or foreseeable technology. Maybe in thousands or millions of years, if civilization survives and continues advancing, we might discover ways to manipulate space-time that we can't imagine now. Maybe exotic matter exists and can be produced and controlled. Maybe there are tricks we haven't thought of, loopholes in the equations we haven't found. Or maybe the universe truly forbids faster-than-light travel and will always be limited to slow journeys measured in decades or centuries. We don't know yet. There are other speculative ideas that get discussed in theoretical physics. Wormholes, for instance. These are shortcuts through space-time, tunnels connecting distant regions. Imagine space-time as a two-dimensional sheet for simplicity, even though it's actually four-dimensional. 2 points on the sheet are separated by a large distance if you travel along the surface. But if you could poke a hole through the sheet and connect the 2 points with a tunnel, a wormhole, you could travel between them much faster. The distance through the wormhole might be much shorter than the distance along the surface. You're not traveling faster than light. You're taking a shortcut through a higher dimensional space. General relativity allows wormholes mathematically. The equations have solutions that describe them. Einstein and Nathan Rosen discovered this in 1935. So wormholes are sometimes called Einstein-Rosen bridges. But just because the equations allow something doesn't mean it exists in nature. The same equations allow negative mass and time machines and all sorts of exotic scenarios, most of which probably don't occur in reality. Wormholes have several major problems. First, they're probably unstable. The equations suggest that a wormhole would collapse almost instantly unless it's held open by exotic matter with negative energy density. The same problematic exotic matter needed for warp drives. You'd need to thread the wormhole with this exotic matter to keep it open. And we don't know if exotic matter exists or can be produced. Second, even if wormholes exist and can be stabilized, they're probably microscopic. The Planck length, about 10 to the negative 35 meters, is the smallest meaningful distance in quantum mechanics. Wormholes, if they exist, might be quantum fluctuations at this scale. Tiny beyond imagining, far too small for anything macroscopic to pass through. Making them larger would require adding enormous amounts of exotic matter and energy. We have no idea how to do that, or if it's even possible. Third, wormholes might be one way. Once you enter, you can't come back, or they might not connect to anywhere useful. A wormhole could connect two regions of space separated by inches rather than light years. Or it could connect to a distant galaxy in a completely random direction. You'd have no way to create a wormhole to a specific destination. You'd be stuck with wherever the natural wormhole leads, if it leads anywhere at all. And fourth, like warp drives, wormholes might allow time travel to the past and create causality paradoxes. If you could traverse a wormhole instantly, you might emerge at your destination before you left from certain reference frames. Or you could use two wormholes in combination to create a closed loop in time. If the universe prevents causality violations, it probably prevents traversable wormholes too. So wormholes are even more speculative than warp drives. Probably impossible, definitely beyond any technology we can imagine building. fun to think about, useful for science fiction stories, but not a realistic path to interstellar travel. Still, the fact that general relativity allows these exotic solutions is interesting. It tells us that space-time is more flexible and strange than everyday experience suggests. The speed of light is a barrier for objects moving through space, but space itself can do things that seem impossible. Space can expand, contract, curve, and maybe even form tunnels. We just don't know how to manipulate it on macroscopic scales. And we don't know if the universe allows such manipulations in practice, even if the equations permit them in theory. Nature might have rules beyond Einstein's equations that constrain what's actually possible. So, where does this leave us? Where does this leave humanity's dream of traveling to the stars? Light-speed travel appears to be impossible for anything with mass. Not just difficult, not just beyond current technology, but fundamentally impossible. A hard barrier written into the laws of physics. The energy requirements approach infinity as you approach light speed. You'd need infinite energy to reach exactly light speed, and infinite energy doesn't exist. The universe simply doesn't provide it. Even if you could somehow reach light speed, the journey would be instantaneous from your perspective. No time would pass for you. You'd exist outside the normal flow of time, in a timeless state where the concepts of duration and experience have no meaning, but the universe would age normally around you. You'd arrive in the distant future, emerging into a time when everyone you knew is long gone. The relativistic effects would be extreme beyond comprehension. Time dilation so severe that time stops completely. Length contraction so complete that all distances become zero. Infinite blue shifting, turning the universe ahead into an impossible wall of infinite energy. Infinite red shifting, making the universe behind vanish into nothing. Your mass becoming infinite. Everything breaks down at exactly light speed. The mathematics produces infinities, which in physics usually means you've pushed the equations beyond their valid range. You're asking them to describe something that can't happen. The closest we could realistically achieve with any foreseeable technology is some fraction of light speed. 10% would be remarkable. 20% would be extraordinary. 50% would require breakthrough technologies we can barely imagine. At 10% of light speed, relativistic effects are small but present. Time runs about 0.5% slower for you than for people on Earth. For every year you experience, Earth experiences about 1 year and 2 days, barely noticeable. The journey to Alpha Centauri would take about 43.7 years from Earth's perspective, and about 43.5 years from yours. Not a huge difference. But it's still an enormous challenge. Accelerating even a small spacecraft to 10% of light speed requires vast amounts of energy and propulsion technology far beyond what we currently have. At 20% of light speed, the effects become more noticeable. Time runs about 2% slower. For every year you experience, about 1.02 years pass on Earth. The journey to Alpha Centauri takes about 21.8 years from Earth's perspective and about 21.4 years from yours, still within a single human lifetime. This might be achievable with future technology. Projects like Breakthrough Starshot are aiming for exactly this. Small probes accelerated to 20% of light speed by powerful lasers. At 50% of light speed, you're firmly in the realm of significant relativistic effects. Time runs about 13% slower. For every year you experience, about 1.15 years pass on Earth. The journey to Alpha Centauri takes about 8.7 years from Earth's perspective and about 7.5 years from yours. A meaningful difference. You'd arrive, having aged noticeably less than people who stayed behind, but the energy requirements are staggering. Accelerating anything to half-light speed requires enormous amounts of power. We'd need breakthrough propulsion technologies. Fusion rockets, maybe. Or antimatter, if we ever figure out how to produce and store it. Or laser sails, pushed by incredibly powerful laser arrays. Even then, we're talking about small probes, not crewed spacecraft. The mass of a human crew with life support and living quarters makes the challenge far greater. These speeds would make interstellar travel possible within human lifetimes, at least for nearby stars. Proxima Centauri, the nearest star, could be reached in a few decades at 20 to 50% of light speed. Not easy, not cheap, but possible in principle. But they still require enormous amounts of energy, technological breakthroughs we haven't achieved, and decades of travel time. And light speed itself remains a barrier we cannot cross. It's not a technological limitation that better engineering might overcome. It's a fundamental law of nature. The universe says no. Physics prevents it by making it require infinite energy, by making time stop and distances vanish, by creating conditions that are logically incoherent. You can't exist at light speed in any meaningful sense because existence requires the passage of time, and time doesn't pass at light speed. Yet there's something beautiful about this limitation, something profound that goes beyond mere frustration at our inability to travel freely. The speed of light is a cosmic speed limit, yes. But it's also the speed at which information propagates through the universe. It's the speed of causality itself. When something happens, when an event occurs, the effects spread outward at light speed. No, faster. The influence of that event expands as a sphere growing at light speed. Everything inside the sphere can be affected by the event. Everything outside hasn't been affected yet. This creates a structure to the universe, a framework of causality. Events are connected by light cones, regions of space-time that can influence or be influenced by a given event. Your future light cone is everything you could potentially affect. Your past light cone is everything that could have affected you. Everything outside these cones is causally disconnected from you, at least for now. Light speed defines the boundaries of causality, the limits of what can influence what. It's the fabric that holds space-time together, that gives the universe its structure. If light speed were infinite, if information could propagate instantly across any distance, the entire universe would be causally connected at every moment. Every event would instantly affect every other event everywhere. There would be no separation, no distinction between here and there, no propagation delay, no time for effects to travel. Everything would be connected to everything else in a single instantaneous web. The universe would collapse into a single point in some conceptual sense. No structure, no sequence, no causality in the way we understand it. Time itself might not exist as we know it. Light speed, being finite, creates separation. It creates distance in a meaningful sense. It creates the passage of time, the delay between cause and effect. It creates the structure of space-time itself, the four-dimensional fabric in which events occur. The fact that we can't travel at light speed is not just a limitation. It's a consequence of the universe having structure, having rules, having consistency, of causality existing and mattering. of time flowing in a particular direction from past to future. If we could travel at light speed, we'd break that structure. We'd exist outside time, in a realm where the journey has no duration, where distances are zero, where the universe collapses into a point. It's not a place we can go, because going there would mean ceasing to exist in time. And existence, our existence as physical beings, requires time. We are creatures of time and space. We're bound by causality, by the progression of moments, by the structure that light speed imposes. We move through time at 1 second per second, always forward, never back. We move through space at speeds far slower than light, taking time to get from one place to another. And that's okay. It's not a limitation to be sad about. It's the framework that makes us real. It means the universe has order. It has rules that apply everywhere, to everything, consistently. It has laws that we can discover and understand. It means physics works the same here as it does in distant galaxies billions of light years away. The same speed of light, the same relationship between space and time, the same fundamental constants. This consistency is what allows us to understand the universe. If the rules changed arbitrarily, if light speed varied from place to place or time to time, we couldn't make sense of anything. We couldn't predict, couldn't model, couldn't comprehend. But because the universe has consistent laws, we can figure things out. We can measure the speed of light and find it's always the same. We can test relativity and find it always works. We can send spacecraft to distant planets and predict exactly where they'll be, years in advance, because the laws of motion don't change. The dream of traveling at light speed is really a dream of transcending our limitations, of becoming something more than physical beings, bound by physical laws, of escaping the constraints that define our existence. But our physicality is what makes us real. Our existence in time is what gives our lives meaning. Our limitations are what make our achievements valuable. Moments matter because they pass. Time is precious because it's limited. Distances matter because they separate us from other places, making travel meaningful. Speed matters because it takes time to cover distance, making the journey an experience. If we could teleport instantly to any location, if we could exist outside time, would our experiences have meaning? Would our choices matter? If you could go anywhere, instantly, at no cost, would going somewhere be an achievement? If you could reverse time and undo any mistake, would your decisions have weight? There's something profound about being limited, about living within constraints. It's what makes our achievements meaningful and remarkable. When we send a spacecraft to Mars, it takes months to get there. Years of planning, billions of dollars, countless hours of work by thousands of people. The difficulty, the time, the effort makes the achievement extraordinary. It means something precisely because it's hard. If we could snap our fingers and be on Mars instantly, would it mean as much? Would we value it the same way? Probably not. Easy achievements don't inspire us. They don't push us to grow and improve. They don't make us proud. The universe gives us challenges, and we rise to meet them. We build rockets that push the boundaries of what's possible. We calculate trajectories with incredible precision. We solve engineering problems that seem impossible. We send probes to every planet in the solar system, each journey a triumph of human ingenuity and determination. And we've done remarkable things while being limited to speeds far slower than light. We've sent probes beyond the solar system. Voyager 1, launched in 1977, is now over 14 billion miles from Earth. It's traveling at about 38,000 miles per hour relative to the Sun. That's fast, by human standards, faster than any spacecraft before it. But it's only about 0.006% of light speed, a tiny fraction. At that speed, it would take over 70,000 years to reach the nearest star if it were heading in that direction, which it's not. It's heading into interstellar space in a different direction, carrying a golden record with sounds and images from Earth, a message to any civilization that might find it billions of years from now, a testament to our existence, our curiosity, our hope that someone else is out there. The fact that Voyager is moving so slowly that it will take tens of thousands of years to reach interstellar distances doesn't diminish the achievement. If anything, it enhances it. We built something that will outlast our civilization, that will carry our message across the galaxy long after we're gone, long after Earth itself might be uninhabitable. That's meaningful, precisely because it's difficult, because it took decades of work, because it required us to push the limits of our technology and understanding. Perhaps one day we'll develop technologies that let us travel at 10 or 20 or even 50% of light speed. Perhaps we'll build generation ships that take centuries to reach nearby stars. Ships where populations live and die during the journey, with descendants arriving who never saw Earth. Perhaps we'll send smaller probes, robotic explorers, that can tolerate the harsh conditions of relativistic travel and report back what they find. Or perhaps we'll discover that we're not meant to travel to other stars, that our future is here in the solar system, spreading across planets and moons and asteroids, building habitats and colonies, but remaining within the gravitational embrace of our sun. There's room for billions or even trillions of people in the solar system, not just on planets, but in orbital habitats, O'Neill cylinders, huge rotating space stations that create artificial gravity and can house millions, Dyson spheres or Dyson swarms, vast arrays of structures collecting the sun's energy. We don't need to leave the solar system to expand and grow and thrive. We could build a civilization spanning the solar system, connected by light-speed communication that takes hours at most, not years or decades. Connected in a way that interstellar colonies could never be. And perhaps that's enough. Perhaps our descendants will look up at the stars, not with a desire to travel there, but with appreciation for their beauty, for their distance, for their separateness. The stars are not ours to conquer or possess. They're not destinations waiting for us. They're other suns with their own systems, their own planets, possibly their own life and civilizations. They're there to inspire us, to make us wonder, to remind us of the vastness of the universe, to make us feel small and large at the same time. Small, because we're confined to one tiny region of space, one solar system in a galaxy of hundreds of billions of stars. Large, because we can understand what we're seeing, because we can measure distances in light years, because we can calculate what would happen if we traveled at light speed, even though we never will. We might never travel faster than light. We might never even travel at a significant fraction of light speed. But we can understand what it would mean to do so. We can work through the mathematics, trace the implications, explore the theoretical possibilities. We can imagine the journey, even if we can never make it. And that understanding is itself a form of transcendence. We're physical beings, bound by physical laws, limited in speed and lifespan and reach. But our minds can explore realms we can never physically reach, We can contemplate infinity. We can imagine traveling at light speed and comprehend why it's impossible. We can understand the mathematics of black holes and the expansion of the universe. We can trace causality across billions of years and billions of light years. Our thoughts are not limited, even if our bodies are. Our imagination can go places our spacecraft never will. And perhaps that's the most important thing: the ability to understand, to comprehend, to know. Even if we can't physically travel at light speed, we can understand what it means. We can trace the implications through mathematics and physics. We can know why it's impossible and what would happen if it weren't. This brings us to an interesting philosophical question about the nature of experience at light speed. What does a photon experience? From our perspective, light takes time to travel. 8 minutes from the Sun to Earth. 4 years from Alpha Centauri to us. Billions of years from distant galaxies. We watch light travel, measure its speed, track its journey across space. But from the photon's perspective, if we can even speak of such a thing, no time passes at all. A photon is created in the core of the Sun through nuclear fusion. Gamma-ray photons, produced by hydrogen, fusing into helium. These photons bounce around inside the Sun for thousands of years, being absorbed and re-emitted countless times, gradually losing energy with each interaction. Eventually, millions of years later, a photon emerges from the Sun's surface as visible light. It travels through space for 8 minutes and 20 seconds from our perspective. Then it enters Earth's atmosphere, scatters off molecules, and finally strikes your eye. It's absorbed by a molecule in your retina, triggering a cascade of chemical reactions that eventually results in a signal to your brain. You see, the Sun. From our perspective, that photon had a journey. It was created millions of years ago, wandered around inside the Sun, finally escaped, traveled through space, and reached your eye. But from the photon's own reference frame, none of that time passed. The photon was created and absorbed in the same instant. No journey, no duration, no experience of travel. The creation and destruction happens simultaneously from the photon's perspective. This is what it means to travel at light speed. Time stops completely. Not slows down dramatically, stops. The Lorentz factor becomes infinite. Time dilation becomes total. For the photon, the universe along its direction of travel is contracted to zero length. The distance from the Sun to your eye is zero from the photon's perspective. They occupy the same location in the photon's frame of reference. And because no time passes, the photon doesn't experience anything between its creation and its destruction. It exists in a single frozen moment, created and destroyed simultaneously. This is deeply strange when you think about it. Light connects different parts of the universe, carrying information from one place to another. From our perspective, light is the messenger, the carrier of signals, the thing that lets us see distant objects. But from light's own perspective, there's no message, no journey, no connection. Just instantaneous transition from source to destination. The 8 minutes we observe the light traveling don't exist for the light itself. This creates an interesting asymmetry. The universe appears different to observers moving at different speeds. We see the photon travel for 8 minutes. The photon experiences zero time. Both perspectives are equally valid within their own reference frames. There's no absolute truth about how long the journey took. It depends on your reference frame. For us, 8 minutes. For the photon, 0. This is the relativity in relativity. Time and space are not absolute, they're relative to your motion. Now imagine you're a hypothetical observer who could somehow travel at light speed while maintaining consciousness and perception. What would you experience? Based on the mathematics, you would experience nothing. No time would pass for you, so you couldn't have experiences, which require time to unfold. You couldn't think, because thinking is a process that occurs over time. You couldn't see, because seeing requires photons to enter your eye and be processed, which takes time. You'd be frozen, or more accurately, you'd exist in a state outside time. The moment you accelerated to light speed would be the moment you arrived at your destination from your own perspective. No journey in between. Like blinking and being somewhere else, except without even the blink. Just instantaneous transition. Your departure and arrival would be the same event in your reference frame. The universe around you would be infinitely compressed in your direction of travel. Every location along your path would occupy the same point. The cosmic microwave background would be blue shifted to infinite temperature. Every photon approaching you would have infinite energy. The universe ahead would be an infinitely bright, infinitely hot point. The universe behind would disappear completely, redshifted to zero energy. You'd be bombarded by infinite radiation from ahead, which would destroy you instantly. If you somehow survived that, you'd still cease to experience time. You'd transition from your point of origin to your destination in a single timeless moment. Effectively, you'd cease to exist as a conscious being during the journey. You might as well be teleported, appearing at your destination with no memory or experience of travel. Actually, it would be worse than teleportation, because everyone else would have aged normally. From Earth's perspective, years or centuries would pass while you made your journey, but you wouldn't experience any of those years. You'd blink out of existence at Earth and blink back into existence at your destination with no subjective passage of time. Meanwhile, Earth would have aged by whatever time it takes light to cover the distance. 4 years if you went to Alpha Centauri. 2.5 million years if you somehow went to Andromeda. This is why light-speed travel is not just impossible, it's incoherent for conscious beings. Consciousness requires time. Thought requires sequential processing. Experience requires duration. At light speed, none of these things exist. You can't be conscious at light speed, because consciousness is a process that unfolds in time. You can't think, because thinking requires one thought to follow another. You can't remember, because memory requires past moments to exist distinctly from present moments. At light speed, past and future collapse into a single eternal present, a timeless now that encompasses your entire journey. You'd be like the photon, existing in a frozen state where creation and destruction are simultaneous, not experiencing anything, just transitioning from one state to another with no journey in between. So even if we could somehow generate infinite energy and accelerate to light speed, we wouldn't experience the journey we imagine. We wouldn't see the stars streaming past at incredible speed. We wouldn't feel the thrill of traveling faster than anything else in the universe. We'd simply cease to exist as temporal beings for the duration, which from our perspective would be zero. This is another reason why light speed is a barrier. It's not just that we can't reach it due to energy requirements. It's that reaching it would mean ceasing to exist in any meaningful sense. You'd be more like a particle than a person, zipping from point A to point B without any subjective experience of the transit. And when you arrived, you'd emerge into a future where everyone you knew is gone, where your entire context has disappeared, where you're a relic from the past, with no connection to the present. The psychological and emotional cost would be devastating, assuming you could somehow maintain your identity through the transition. This is why most serious proposals for interstellar travel focus on sublight speeds. 10 to 20% of light speed is challenging, but at least makes sense. You'd experience time passing. You'd age during the journey. You'd have memories of the trip. You'd arrive having lived through the voyage, not having skipped over it entirely, and the time dilation would be manageable. At 20% of light speed, about 2% time dilation. For every 10 years you experience, about 10.2 years pass on Earth. Noticeable, but not devastating. At 50%, about 15% time dilation. For every 10 years you experience, about 11.5 years pass on Earth. More significant, but still within the realm of human understanding. You could maintain some connection to Earth, send messages back and forth, stay in contact with your origin civilization. The communication delay would be frustrating. Years between message and reply, but at least it would be possible. At light speed, communication becomes meaningless because you don't experience time during the journey. You can't send messages because sending requires time to pass. You can't receive them because receiving requires time to process the signal. You'd be completely isolated from the rest of the universe during your instantaneous journey. Cut off from causality, existing in a bubble outside space-time. This isolation is another aspect of light speed's impossibility. The universe is held together by causal connections propagating at light speed or slower. Events influence other events through signals that travel no faster than light. This creates a web of causality connecting everything. At light speed, you'd exist outside that web, causally disconnected from everything, not influencing or being influenced by anything during your journey. Like a ghost passing through the universe without touching it. When you emerged at your destination, you'd suddenly rejoin the causal web, but you'd have missed everything that happened in between. Years or centuries of history erased from your personal timeline. You'd be out of sync with the universe, temporally displaced, a stranger in a strange time. So light-speed travel is not just physically impossible, it's experientially incoherent. It doesn't make sense for conscious beings who exist in time. It's a limit not just on our speed, but on the very concept of travel as we understand it. Travel implies a journey, a passage from origin to destination, a process that takes time. At light speed, there is no journey, just instantaneous transition, which isn't travel in any meaningful sense. It's more like disappearing from one location and appearing at another with no continuity between them. And this gets at the heart of why the speed of light is special. It's not just another speed, faster than we usually go, but achievable with enough effort. It's a fundamental boundary in the structure of space-time, a limit that separates time-like trajectories, paths that normal matter can follow, from null trajectories that only massless particles can take, and from space-like intervals that connect events that can't influence each other at all. Time-like paths have a well-defined duration. You can set a clock to measure the time along the path. Different observers might disagree about how much time passed. That's relativity, but all agree that some time passed. The path has a temporal extent. Null paths, like the path of a photon, have zero duration. No clock ticks along a null path. Time doesn't pass. The path connects two events, emission and absorption, but from the photon's perspective, they're simultaneous. Space-like intervals connect events that are too far apart in space for light to travel between them in the time available. These events can't influence each other. they're causally disconnected. Light speed is the boundary between these categories. It separates what can travel from what cannot, what can influence from what cannot, what experiences time from what doesn't. It's not arbitrary. It's built into the geometry of space-time itself, the mathematical structure that describes how space and time relate to each other. In this structure, light speed is invariant. Every observer measures the same value regardless of their motion. And this invariance is what forces all the relativistic effects we've discussed: time dilation, length contraction, the energy requirements, the impossibility of reaching light speed with massive objects. All of these follow mathematically from the single postulate that light speed is constant for all observers. Einstein built special relativity on this foundation. He asked what the universe would need to be like if light speed is truly constant. And the answer was that space and time must be flexible, adjusting to keep light speed fixed. The rest follows inevitably from that starting point. General relativity extended this to include gravity and acceleration, showing that space-time itself is curved by mass and energy. But the core insight remains: light speed is special. It's the conversion factor between space and time in the geometry of space-time. It's the speed at which causality propagates. It's the maximum speed for anything with mass. And it's unreachable by any physical process that involves accelerating mass. Understanding this helps us see why light speed isn't just a technical challenge to overcome. It's a fundamental feature of reality. The universe is structured this way. Space-time has this geometry. Light speed is what it is, and nothing with mass can reach it, because that's how space-time works. We can't change it any more than we can change the fact that triangles in flat space have angles summing to 180 degrees. It's a mathematical truth about the structure we live in, and that's okay. More than okay, it's necessary. If light speed weren't constant, if we could exceed it, causality would break down. Effects could precede their causes. Time travel to the past would be possible, creating paradoxes. The universe would become inconsistent, chaotic, impossible to understand. The speed of light being a fixed limit is what keeps the universe sane and comprehensible. It's what allows physics to work. What allows us to make predictions and test them. What allows cause and effect to have meaning. So we should be grateful for this limit, strange as that might sound. It's not holding us back. It's holding the universe together, giving it structure and order and laws that we can discover and use, allowing us to exist as conscious beings who experience time and can understand our place in the cosmos. So, what would really happen if you traveled at light speed? From your perspective, nothing. The journey would be instantaneous. Time would stop. Distances would shrink to zero. You'd leave and arrive in the same moment, with no experience of travel in between. From everyone else's perspective, you'd be moving at light speed, taking years or centuries or millennia to reach your destination depending on how far it is. They'd watch you age slowly or not at all while they aged normally. When you arrived, you'd emerge into their future, a time traveler who skipped forward through the years. The universe in front of you would be compressed into an infinitely energetic point of radiation. The universe behind you would vanish into darkness. Space and time would become so warped that the very concepts lose meaning. You'd exist in a state outside normal space-time, neither here nor there, neither now nor then. But you can't actually do this because you have mass and accelerating mass to light speed requires infinite energy, which doesn't exist. The universe prevents you from reaching light speed by making it require infinite energy. It's a hard limit, a boundary you cannot cross. Physics says no, and there's wisdom in that boundary. It preserves causality, maintains the structure of space-time, keeps the universe consistent and comprehensible. It ensures that time flows, that events have sequences, that causes precede effects. It's the rule that makes the universe work. So we'll never travel at light speed. We'll never experience the journey as instantaneous. We'll never compress the cosmos into a point. We'll remain here, moving through space at modest speeds, experiencing time at normal rates, aging year by year, living our finite lives in this vast universe. And maybe that's exactly as it should be. Maybe the limitations are not obstacles but features, not barriers, but boundaries that give structure and meaning to existence. The speed of light is not just a number, it's the framework of reality itself. It's the maximum speed of causality, the cosmic speed limit, the boundary between possible and impossible. And understanding that, truly understanding what it would mean to travel at light speed and why we can't, gives us insight into the fundamental nature of the universe. We're not separate from the universe, we're part of it, subject to the same laws, made of the same matter, following the same rules as stars and galaxies and photons. And those rules, those limits, are what make us real. Thank you for joining me on this journey through the physics of light speed. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the cosmos. And remember, we might never travel at the speed of light, but we can understand it. And that understanding connects us to the deepest truths of the universe. Good night.